first speaker is Cumrun Vafa, who will speak on geometric metastability.
Thank you. Well, first of all, I'd like to thank the organizers for organizing such a wonderful conference in such a beautiful country. And it's a great pleasure for me to be able to give a talk in this conference. I hope my voice is not completely incomprehensible. I have some kind of a cold. So I'm going to talk about a couple of works, and one work to appear with the collaborators Aganagic and Beam and Seo and Heckman. So breaking supersymmetry in string theory remains a challenge. There has been recent progress in going away from supersymmetric situations in string theory, and two notable directions that have been pursued recently are construction of metastable vacua without supersymmetry and non-supersymmetric studies of non-supersymmetric extremal black holes. We have heard about both of these aspects in this conference. Now, the focus of my talk is going to be the first aspect, the construction of the metastable vacua without supersymmetry. Given the fact that the geometry and supersymmetry have played a prominent role in the development of string theory, it's natural to try to somehow use one to break the other in the context that we want, maybe connection with more realistic models in string theory. So indeed in this talk we try to use geometry to break the supersymmetry, and we also use the implications of large M duality in such a picture. So far, the only examples in string theory which break supersymmetry, the main ones involve metastable vacua. There are also some stable ones with ADS structure. But the more interesting ones are the metastable ones initiated by the work of KKLT and many works to follow. Now, the idea of having a metastable vacuum is actually a very natural idea, it turns out, in field theory. And they're abundant in field theory. The first example of this connection I would like to bring to your attention is even the simplest gauge theory in 4-dimension, or the most canonical one in some sense. If you take a UN Yang-Mills, pure Yang-Mills theory with no supersymmetry at all, at large n it has order n vacua, metastable vacua, which become exactly stable as n goes to infinity. So this fact, which was noted by Witten already in 1980, is an amazing fact about the proliferation of metastable vacua, even in very ordinary systems without any real stuff except for gauge fields. The second class of examples, if we believe supersymmetry plays any role in our world, which we think it does, is constructions of metastable vacua in the context of supersymmetric theories, which was actually shown by this beautiful work of interrogated Seiberg and Shi, and the subsequent works that we heard about from Hiroshi in his talk, that these are very typical situation in the context of supersymmetric vacua as well. So the idea of metastability, by all means, in field theory is a natural idea, and in string theory it seems to be the way we are trying to connect in a natural way to the real world. And perhaps the natural way to realize these in the context of supersymmetry, in the context of string theory, is to use brane and anti-branes. For example, a very simple idea would be we take a 4-dimensional space-time and we have some internal geometry like a Calabi threefold, and we stack up the branes and anti-branes filling the space-time and corresponding to points in the internal geometry. So you have some branes, some positions of the D3 branes, noted here by these blue crosses, and the red crosses being the anti-branes. This would break supersymmetry in particular. Or we can do something more fancy if you wish. We can still use the branes and anti-branes to fill the space-time, but wrap these, if you have higher dimensional branes like D4, D5 or whatnot, to wrap cycles inside the Calabia, and again you can have branes and anti-branes to break supersymmetry. Now, if we just do the most naive way, this won't work, of course, because the most naive way will involve attraction between brane and anti-brane, and they would not be stable, they would not be even metastable, they would just attract one another and annihilate. One could use fluxes to remedy this, and Shomit discussed it in his talk. Here I will talk about another way to use geometry to stabilize branes and anti-branes. And the idea would be to look like geometries. Instead of looking like this cylindrical picture, we'll have some kind of necks that you can kind of wrap these branes around these necks and stabilize them. It's a very simple idea. So we will consider a situation like this where we have a geometry which have these regions where you can put branes and anti-branes. And in this way we will have a situation where, despite the fact that supersymmetry would be broken, they would be metastable, because they would have to, in order to annihilate, to reach equilibrium, they will have to climb some barrier. So you will have to, the branes will have to move in geometry. They will have to have a higher tension as they move in this geometry from one place to another. And this causes energy. So you can basically translate the geometry shape to a potential barrier. So geometry induces a potential barrier which causes the metastability for this guy to go and find the other guy to get the annihilation. So it's a very simple idea. Geometry is directly translated to the potential. But for this mechanism to work, there must be such cycles that are basically, these necks should exist. And from the picture I drew, it looks a bit artificial. How would you arrange a geometry to have such necks? It looks a bit fine-tuned. And perhaps the welcome fact is that these are very typical in Calabi-Yau threefolds. In fact, the very generic statement about the Calabi-Yau threefold was the fact that they always come with these isolated necks. And for example, if you look at the famous Calabi-Yau threefold, the quintic, it has, for example, in the generic moduli 2,875 of these necks. So you can, they not only come, they come in abundance automatically without you working too hard to get them. And you can put your branes and anywhere you want on these 2,875 necks. So we are not fine-tuning in that sense. So the simplest local geometry are these P1s, which is locally these P1s look like the blown up conifold, the situation that we have, the S2s, where we can wrap the n branes around S2. So in this context, we'll be talking about D5 branes, where they be filling the space-time, and they will be wrapping, in addition, the two spheres that will be isolated inside Calabi-Yau. We know that the low energy description of the degrees of freedom living on the brane involve n equals to 1 supersymmetric theories, UN gauge theory. So Calabi-Yau breaks half the supersymmetry, and the brane kills, Calabi-Yau breaks it, sorry, to n equal to 2, and the brane kills another half to n equals to 1. Now the large and dual descriptions of these geometries have been studied, and in particular we know that the geometry undergoes a transition, namely the S2 shrinks and the S3 grows, where the branes that we had over here get translated to the fluxes that we have on the other side. And the way that the branes make their appearance is through the flux through this dual three-cycle that surrounded them before the transition. Certain geometric facts and low energy aspects can be understood by studying the superpotential. Namely, we consider on the large and dual description of this brane the modulus of this S3, which is characterized by a field S, and you can describe this by existence of a superpotential, which is this familiar Veneziano-Yankee superpotential, whose critical points will give you the size of the S3, so it will rigidify it. And this comes naturally from the special geometry of the n equal to 2, namely, it basically is a combination of the periods of the Calabi-Yau. So the Calabi-Yau geometry dictates the superpotential that's generated, and the critical points of W give you the nice critical points, and we can get the familiar story that we know from the Veneziano-Yankelevich for n equals to 1 UN gauge theory, where S gets identified to the linear bilinear on the gauge theory side. So in our case, we consider large n limit and conjecture that if you do this wrapping of the branes for each individual 2 cycles, so here on this side we're talking about the geometry where we have wrapped branes over these S2s that we have, and we conjecture that in the large n it's better to describe the same system with a dual geometry where S2s have been replaced by S3s with the corresponding fluxes through them. Except that the fluxes might have opposite signs, namely the signs that will be correlated with the corresponding branes. Whether you have branes, you get positive flux and in the appropriate sense of orientation, and the other one you get negative. So that's our conjecture. To be more precise, I would not be discussing in this talk compact cases. I will, from the beginning, talk about non-compact case, which in particular means I would have nothing to say in the context of gravity. I'll be only talking about the local geometries. So for me, gravity will not be dynamical. So we'll talk about the non-compact Calabi-Yau threefold, and we look at geometries which look like hypersurface in C4 of the form u squared plus v squared plus y squared is w prime of x squared in a 4-dimensional space given by u, v, x, and y. And we take this w prime to be a product, some kind of polynomial with n zeros. So these geometries will have naturally 2 spheres built in them. If you think about u, v, and y as parameterizing in the real sense a 2-sphere with a given value, so think about x as being fixed. Once you fix x, this gives you a 2-sphere in the real section of it. So you can think about it as a 2-sphere varying, which here I'm denoting by this region varying over x, where the size of the 2-sphere varies depending on where you are in x. The minimal sizes will appear when the w prime will have small size, for example 0. So the critical points here will be where the neck actually appears, is precisely the critical points of this w prime in this geometry, where you get conifold-like geometries, where you can have a blob, where you can actually have a 2-sphere attached to it. So this is a very simple way where you can locally have a bunch of these conifolds appearing for yourself. So you indeed have these kinds of geometries, and you can see that the profile of the geometry, namely the size of S2, is dictated by this superpotential or w prime, this function that dictates the geometry. The case when only branes wrap cycles in this geometry, not anti-branes, is a case that has been studied quite a bit a while back. And so this actually ended up being related to a very simple gauge theory system, namely it turned out to be related to n equals to 1 un gauge theory with a superpotential, with an adjoint field phi, with the superpotential for the adjoint w of phi, where this w is exactly the same function that appears in geometry. So the geometry encodes the superpotential, and this gave a way to realize these systems in string theory, and was studied by a number of people. So our aim here is to study basically these, except that, well, it would be useful to remind ourselves how it worked in the supersymmetric case. In the case of the supersymmetric case, you looked at the critical points of this gauge system, w prime phi is 0, and you could then distribute the eigenvalues of phi depending on where you want to put the branes among these n different critical points of w. So depending on where you put them, how many you put where, these points that corresponded to where the P1s were in the large n dual open up a cut which corresponds in the Calabi-Yau geometry to developing a 3-sphere where the fluxes go through them depending on how many of the eigenvalues of the phi you distribute and put through each one of these cuts. And so these correspond to the geometries where you first of all before the transition you distribute the branes on each P1 according to this distribution of the eigenvalues, and the large n dual where each of these branes have been disappeared to the fluxes. And then you study the generalization of this superpotential, where again you have fluxes times which are obtained by the flux number times the dual periods minus tau times the sum of these sizes of each of these S3s, which I called here by SI, and studying the superpotential there and the critical point of it led to some information about n equals to 1 low energy dynamics. The nice feature of this is that the computation of the prepotential in this context, which determines W, is actually something which can be done in an integrable structure. That is, the superpotential encodes itself how you can compute this prepotential, and therefore the potential, the superpotential of the gauge theory dictates F0, which in turn dictates the superpotential which describes the low energy degrees of freedom that you get on the large n side. And it's captured by a simple matrix model, and the planar diagram, summing over planar diagrams, captures F0 of S. So the prepotentials can be captured by a simple matrix integral. So just to recap, we started with a potential in the gauge theory, which corresponds to the same thing in the Calabi-Yau geometry. That W encodes the geometry of Calabi-Yau. That potential and the geometry of Calabi-Yau lead to a computation of the prepotential, which can in turn lead to Venetian-Yankelevich-like superpotentials, which you extremize to get the low energy dynamics corresponding to the large n dual. So large n duality dictates the structure here. Okay, so that was the background. So we want to do a similar story, except now we want to replace some of the branes with anti-branes. So we have branes and anti-branes. From the outset, it should be clear that we are not talking about this as a gauge theory system. It does not mean it makes no sense to talk about negative rank of these gauge groups. So we are not making a claim that this is related to a gauge system. This is unlike the case, for example, studied by ISS, where they actually had a gauge system in the system. Here is a stringy realization of supersymmetry breaking, which won't have a naturally finite degree of freedom in terms of gauge system. But nevertheless, we can describe it and see what large n techniques will teach us about this non-supersymmetric system. So we have branes and anti-branes. As I described, there's a potential here. Now, we know that this is not going to be a stable situation, but we can study it. Namely, we can make a natural conjecture, as I mentioned, that these branes are replaced by fluxes at the large n dual description, and we can compute the low energy dynamics of this theory by making a very simple postulate. That is, you compute the superpotential and just replace the flux number instead of plus with a minus, which is a very benign operation in some sense. You just say the fluxes change sign. So if you have N1 branes and N2 anti-branes, all you're saying is that the sign there has become negative. So you look at the potential, which is the gradient of W squared. There's a natural metric which comes from the n equal to 2 Keter potential, the prepotential, the special geometry, which again is dictated by the prepotential. So the prepotential, which is captured by the geometry, dictates both the kinetic term, the metric here, and the superpotential term. So in some sense, we have so thinking about it in terms of integral models, you start with a matrix integral, just a matrix, and it dictates for you a natural automatic potential. And now what we want to do is actually look at critical points of this V. And the critical points of this V would naturally, we expect them to have critical points which break supersymmetry, because after all, we studied with a gauge system which was not supersymmetric, so we expected to break it. So we look for the critical points of this, and indeed the natural thing to consider is the limit where these cuts are far away. So branes and anti-branes are far away from each other. So in other words, the delta which separates where the branes and anti-branes are, if they are far away, you roughly speaking get two decoupled n equals to 1 systems. Each one preserves its own supersymmetry. So you have roughly the old story of 2 n equals to 1s, and the supersymmetry breaking should be suppressed when delta is sufficiently large. In other words, near each of these critical points, the prepotential looks like the conical type, xi squared log xi, where xi is just related to the corresponding size of the S3, and you can extremize them as two decoupled system naively. But actually, in this context, we have much more information. We can actually study it for finite delta, but just at least in the large n limit, in the planar limit, because we can actually compute the V by summing up over all these planar diagrams using the matrix integral. So we have the full information about computation of this potential. So this will encode situations where you're summing up in a non-supersymmetric situation, where you have branes ending on some of the boundaries of the worksheet ending on the branes, some ending on anti-branes, and so forth. And using this, you can compute the corresponding potential in the same way I just mentioned before. So for example, at one loop, you can compute the contributions. And there are two situations in the analysis diagram contribution. The ones ending on branes, the ones ending on anti-branes, and the ones which one end ends on branes, the other one ends on anti-branes. And it is this piece, of course, which breaks the supersymmetry, which communicates the fact that brain and anti-brain exist there together. So if you look at the structure here, you find that the vacua is looks very similar to what you would expect for n equals to 1 situation, except that you have some complex conjugation going in terms of the parameters. It looks like the natural variables for the brains and the anti-brains are complex conjugates of each other, which is not that surprising. In a sense, it's related to the fact that the fermions which come from this channel have the opposite chirality, and so the theta angle runs in the different way than you would expect. The real part runs the same way. So the absolute value of this would have run the same way as you would have expected, but the phase runs in a funny way, and that's dictated by the fact that there is the chirality flip because of the brain-anti-brain boundary condition on the annulus. Note also that there are n1 times n2 solutions here. So we have found discrete solution, but not a unique one. So we started with a brain, n brain, and n1 brain and n2 anti-brains. We did not find a unique large n dual, but n1 times n2 discrete choices, just like n equals to 1 supersymmetric theory. But this sounds surprising because in the non-supersymmetric case, you would not expect to have degeneracy for no reason. And indeed, we will find in a minute that this degeneracy, which at this level is there, disappears when you consider higher order corrections. But before I talk about that, I just want to note that to this order already you can study the supersymmetry breaking. We have 5 minutes. Okay. So the supersymmetry breaking already can be studied at this level, and you can find that by studying the boson and fermion mass degeneracies, you see that they are not equal. And here I'm drawing the masses of the bosons, which are these blue curves, versus the red one, which are fermions, as a function of the ratio of the brain-anti-brain. If there are a lot more brains than anti-brain, is almost supersymmetric, and the two extremes, and the maximal breaking when they are equal in number. And they can also decay as the usual way by using a D5 brain, which goes between them. But since I don't have much time, less than 5 minutes, I have to speed up a little bit. I'm going to talk about the phase structure, which is what happens when you consider these higher order terms beyond the one loop. And so you can have n cuts and study what happens, what we get for the phase structure in this story. So let's study a very simple case where you have n brains and n anti-brains in the cut, equal number but opposite in sign. So you have n flux n unit on one side and minus n on the other side. By symmetry, you expect the size of S1 and S2 to be equal by the Z2 symmetry of the exchange. So you at least the absolute value, you think they should be the same, and indeed they are. So you can actually study the potential as a function of S, the one I told you about. And to one loop, you find the one I mentioned before, which has a critical point S star. Now you can consider higher loops. In fact, you can consider arbitrary higher planar diagrams that you wish. But already it turns out at 2-loop level, when you have a worksheet ending on 2 brains and 1 anti-brain, this potential changes qualitatively, and you find a critical point bends down. You find a new critical point, and it turns out when you make n large enough, when you make the number of brains and anti-brains large enough, you actually will lose metastability. That critical point comes and eats away the other one, and you basically have it runs away. So metastability is lost at large n level, at large n. So that's the lesson we learned. We could not have necessarily anticipated this. At the 2-loop order computation to Venetian and Clevich potential, this already is consistent with that. Also, it turns out that n1 times n2 degeneracy I told you about disappears, the degeneracy that you have in the supersymmetric case. So if you look at the orientation of this glue ball feeds S1 and S2, there were n1 times n2 choices, depending on which phase you choose for these solutions, which I'm denoting here by these angles. It turns out that already at 2-loop, there's a potential generated for the would-be axion, which is given by the formula here, n squared cosine theta over n. This is the kind of structure was expected already by this paper of Witten I mentioned, which suggests that when you change the theta angle, what is actually a critical point changes. So first of all, out of all these choices of orientation, it wants to align the cuts. The cuts get aligned, and if you change the angles, when one of them is going up, the other comes and takes the place of the first one. So they want to be as parallel as possible. And so changing the theta angle, you decay to new vacua in order to make them as aligned as possible. And this explains why this cosine theta over n does not have the periodicity of 2 pi. It's not analytic in the sense that you have to replace it by the new vacuum which plays that role. So we can also consider some amusing multicut geometries, and they have interesting geometries that you can have. As I mentioned, in the context of Calabi-Yau, you will have multicut geometries. There are a huge number of them. So it will be interesting to study what happens there, and there are some interesting qualitative features which are noteworthy. It turns out that if you put, for example, branes on one end and anti-branes on the other end, it turns out that, and if you don't put any other branes in the middle of these, so you have geometries, branes, brain, nothing, anti-brain, the brain has to go over and kill the other brain to make it supersymmetric, but it turns out it is actually obstructing. The geometry is obstructing this process. So in fact, there's no direct mechanism to jump. It will go through steps. It will first have to go over there and then hop to the next one and so forth. So this is a situation where, roughly speaking, the potential would look like have a structure like it goes from one metastable to another one, closer and closer, and the geometry is creating this outer layer of obstruction to stabilization. So you can have multi-reasons for metastability. Metastability based on geometries in this way as well. So since I've basically run out of time, I should just finish with concluding remarks that there have been a number of papers, interesting work that I won't be able to review here, but let me just mention one interesting work also that was done by this group, by Marsano, Padiamos, and Shigemori, where they took the mirror of this geometry in type 2A and lifted it up to M theory. And in this context, they found this geometry being realized by M5 branes. So in the supersymmetric context, the M5 branes involve a holomorphic embedding of M5 brane inside the flat space. What they found was, in this context, the supersymmetric brane convex, all that happens in a very nice way, the holomorphic Riemann surface is replaced by a harmonic Riemann surface. So it's harmonic but not holomorphically embedded, and that's why those will eventually decay to holomorphic ones. There are many open questions. The most urgent one, I would say, is embedding this story to the compact case. And already in this case, there are some interesting subtleties that we heard about from Mike Douglas about the corrections that you will encounter to Kähler potential that will be crucial to better understand. There are other geometries that could be studied, and some interesting work has already been done in work to appear by Aganovich and company. It's also interesting to understand what is the fate of this metastability. As I mentioned, when you make the n larger and larger, these cuts get bigger and bigger, and suddenly you lose metastability before the cuts touch. And so it wants to go to the direction of the whole cuts touching each other, and you create another S3 from the middle S3, but what happens there, what is the fate of this metastability is not quite clear. Also, the connection to open string tachyon is not clear. What happens when you bring these branes together, close together? The regime I talked about was involving the regime where these are far away from each other. It would be interesting to understand the connection to open string tachyons when you bring the branes and anti-branes close together. And I have a hunch that this whole story is not unrelated to the non-supersymmetric black holes, extremal black holes, that we heard about in the talk that Trivedi gave, but that connection remains to be better explored. So I'll stop here. Thank you.
Questions or comments? Nati. Wait for the micro. Sorry, use the micro, please.
I don't understand your comment about the field theory description of it. If we go to high enough energy, we should see the quarks and the gluons of the 2SUN, right? So at that point, when gravity is irrelevant, so there must be a field theory relevant at that energy scale, which flows in the infrared to what you're discussing.
Well, the situation is similar to having, let's take a simpler situation where you have ND3 brane and M anti-D3 brane. You would think that there's a UN plus M gauge theory, but there's none. I mean, people have tried to write down a field theory involving brane and anti-brane D3 branes, and there's no satisfactory finite degree of freedom. Of course, there's open string field theory you can write down. So there is that, of course. But for finite truncation, it's hard to imagine a situation where you can decouple only a finite degree of freedom, because if you think about N1 brane and N2 anti-brane, it should be in the same universality as UN1 minus N2 theory, but why couldn't you go higher? It should be able to go up, namely it should be also include N1 higher and N2 higher. There's no natural way to break it. In other words, this creating a brane-anti-brane pair is natural, and there's no way to naturally write down a finite degree of freedom.
I guess I'm not asking about UN plus M, UN minus M. I'm asking about UN1 cross UN2 with something else.
Yeah. Yeah, so the part of the reason that this cannot be done in a natural way, there are many arguments, but one simple argument, which is actually not unrelated to the issues that I think you also studied in the context of the embeddings of your models in string theory, which is the fact that the running of the coupling at infinity goes like n1 plus n2, an absolute value in brain and anti-brain, whereas when they annihilate, the running should go to n1 decreased number, so the running at infinity is changing. So there's no decoupled system involving this system, because otherwise you would have not to touch the ultraviolet. So the fact that it runs all the way to infinity is another symptom that this is not decoupled system. It involves all the stringy degrees of freedom.
Okay, Schmidt. Wait for the mic, please. Over there.
Yeah, a lot of the simple systems in field theory with metastability, or some of the systems with branes in flux, in the non-supersymmetric vacua, there are light Goldstone modes, Goldstone bosons of some broken symmetries. Do you have any insight as to whether geometric transitions could possibly capture SUSY breaking states that also have light Goldstone modes? Most of these really have a mass gap except for the Goldstino.
I don't have anything particular to say about that. In these contexts, we of course have Goldstinos in the usual sense, and they pick up mass the right way, but nothing more than that.
Any further points? Sorry? Yes.
If you look at this limit where the two cuts get very close to each other,
yes,
you could probably formulate in some dual variables where you take the cycles between the two edges. Do you get any easy description in terms of some dual theory?
Yes, in fact we do believe that that's the right picture, namely you go to a dual description, and we think that what might happen is that you actually undergo further transition where an S2 pops out. So here you have an S3 and you go back to a flux through there. But this will involve a non-Calabi geometries, which perhaps is not surprising in the context where you have fluxes and the kind of geometries we have heard about. So it's kind of a natural conjecture to expect that you will have more generalized geometries. We don't have enough, part of it, we don't have enough intuition to what I expect. And we don't have enough intuition to these non-Calabi geometries to say something more concretely. I think it's a very interesting question to study.
Okay, let's thank Cumrun again. Next speaker will